Chapter 4, Ape Beds, Dinosaurs, and Napping with Half a Brain. Who sleeps, how do we sleep, and how much? WHO sleeps. When did life start sleeping? Perhaps sleep emerged with the great apes? Maybe earlier. In reptiles, are there aquatic antecedents, fish? Short of a time capsule, the best way to answer this question comes from studying sleep across different phyla of the animal kingdom, from the prehistoric to the evolutionarily recent. Investigations of this kind provide a powerful ability to peer far back in the historical record and estimate the moment when sleep first graced the planet. As geneticist Theodosius Dobzhansky once said, nothing in biology makes sense except in light of evolution. For sleep, the illuminating answer turned out to be far earlier than anyone anticipated, and far more profound in ramification. Without exception, every animal species studied to date sleeps, or engages in something remarkably like it. This includes insects, such as flies, bees, cockroaches, and scorpions, fish, from small perch to the largest sharks, amphibians, such as frogs, and reptiles, such as turtles, Komodo dragons, and chameleons. All have bona fide sleep. Ascend the evolutionary ladder further and we find that all types of birds and mammals sleep, from shrews to parrots, kangaroos, polar bears, bats, and, of course, we humans. Sleep is universal, even invertebrates, such as primordial mollusks and echinoderms, and even very primitive worms, enjoy periods of slumber. In these phases, affectionately termed lethargous, they, like humans, become unresponsive to external stimuli, and just as we fall asleep faster and sleep more soundly when sleep deprived, so too do worms, defined by their degree of insensitivity to prods from experimenters. How old does this make sleep? Worms emerged during the Cambrian explosion, at least 500 million years ago. That is, worms and sleep by association predate all vertebrate life. This includes dinosaurs, which, by inference, are likely to have slept. Imagine diplodocuses and triceratopses all comfortably settling in for a night of full repose. Regress evolutionary time still further and we have discovered that the very simplest forms of unicellular organisms that survive for periods exceeding 24 hours, such as bacteria, have active and passive phases that correspond to the light-dark cycle of our planet. It is a pattern that we now believe to be the precursor of our own circadian rhythm, and with it, wake and sleep. Many of the explanations for why we sleep circle around a common, and perhaps erroneous, idea: sleep is the state we must enter in order to fix that which has been upset by wake. But what if we turned this argument on its head? What if sleep is so useful, so physiologically beneficial to every aspect of our being, that the real question is, why did life ever bother to wake up? Considering how biologically damaging the state of wakefulness can often be, that is the true evolutionary puzzle here, not sleep. Adopt this perspective, and we can pose a very different theory. Sleep was the first state of life on this planet, and it was from sleep that wakefulness emerged. It may be a preposterous hypothesis, and one that nobody is taking seriously or exploring, but personally I do not think it to be entirely unreasonable. Whichever of these two theories is true, what we know for certain is that sleep is of ancient origin. It appeared with the very earliest forms of planetary life. Like other rudimentary features, such as DNA, sleep has remained a common bond, uniting every creature in the animal kingdom. A long-lasting commonality, yes. However, there are truly remarkable differences in sleep from one species to another. 4 such differences. In fact, one of these things is not like the other. Elephants need half as much sleep as humans, requiring just 4 hours of slumber each day. Tigers and lions devour 15 hours of daily sleep. The brown bat outperforms all other mammals, being awake for just 5 hours each day, while sleeping 19 hours. Total amount of time is one of the most conspicuous differences in how organisms sleep. You'd imagine the reason for such clear-cut variation in sleep need is obvious. It isn't. None of the likely contenders: body size, prey-predator status, diurnal, nocturnal, usefully explains the difference in sleep need across species. Surely sleep time is at least similar within any one phylogenetic category, since they share much of their genetic code. It is certainly true for other basic traits within phyla, such as sensory capabilities, methods of reproduction, and even degree of intelligence. Yet sleep violates this reliable pattern. Squirrels and Degoosare are part of the same family group, rodents, yet they could not be more dissimilar. In sleep need, the former sleeps twice as long as the latter, 15.9 hours for the squirrel versus 7.7 hours for the degu. Conversely, you can find near identical sleep times in utterly different family groups. The humble guinea pig and the precocious baboon, for example, which are of markedly different phylogenetic orders, not to mention physical sizes, sleep precisely the same amount, 9.4 hours. So what does explain the difference in sleep time, and perhaps need, from species to species, or even within a genetically similar order? We're not entirely sure. The relationship between the size of the nervous system, the complexity of the nervous system, and total body mass appears to be a somewhat meaningful predictor, with increasing brain complexity relative to body size resulting in greater sleep amounts. While weak and not entirely consistent, this relationship suggests that one evolutionary function that demands more sleep is the need to service an increasingly complex nervous system. As millennia unfolded and evolution crowned its current accomplishment with the genesis of the brain, the demand for sleep only increased, tending to the needs of this most precious of all physiological apparatus. Yet this is not the whole story, not by a good measure. Numerous species deviate wildly from the predictions made by this rule. For example, an opossum, which weighs almost the same as a rat, sleeps 50% longer, clocking an average of 18 hours each day. The opossum is just 1 hour shy of the animal kingdom record for sleep amount, currently held by the brown bat, who, as previously mentioned, racks up a whopping 19 hours of sleep each day. There was a moment in research history when scientists wondered if the measure of choice, total minutes of sleep, was the wrong way of looking at the question of why sleep varies so considerably across species. Instead, they suspected that assessing sleep quality, rather than quantity, time, would shed some light on the mystery. That is, species with superior quality of sleep should be able to accomplish all they need in a shorter time, and vice versa. It was a great idea, with the exception that, if anything, we've discovered the opposite relationship: those that sleep more have deeper, higher quality sleep. In truth, the way quality is commonly assessed in these investigations, degree of unresponsiveness to the outside world and the continuity of sleep, is probably a poor index of the real biological measure of sleep quality, one that we cannot yet obtain in all these species. When we can, our understanding of the relationship between sleep quantity and quality across the animal kingdom will likely explain what currently appears to be an incomprehensible map of sleep time differences. For now, our most accurate estimate of why different species need different sleep amounts involves a complex hybrid of factors, such as dietary type, omnivore, herbivore, carnivore, predator, prey balance within a habitat, the presence and nature of a social network, metabolic rate, and nervous system complexity. To me, this speaks to the fact that sleep has likely been shaped by numerous forces along the evolutionary path, and involves a delicate balancing act between meeting the demands of waking survival, e.g., hunting prey, obtaining food in as short a time as possible, minimizing energy expenditure and threat risk, serving the restorative physiological needs of an organism, e.g., a higher metabolic rate requires greater cleanup efforts during sleep, and tending to the more general requirements of the organism's community. Nevertheless, even our most sophisticated predictive equations remain unable to explain far-flung outliers in the map of slumber. Species that sleep much, e.g., bats, and those that sleep little, e.g., giraffes, which sleep for just 4 to 5 hours. Far from being a nuisance, I feel these anomalous species may hold some of the keys to unlocking the puzzle of sleep need. They remain a delightfully frustrating opportunity for those of us trying to crack the code of sleep across the animal kingdom, and within that code, perhaps as yet undiscovered benefits of sleep we never thought possible: to dream or not to dream. Another remarkable difference in sleep across species is composition. Not all species experience all stages of sleep. Every species in which we can measure sleep stages experiences NREM sleep, the non-dreaming stage. However, insects, amphibians, fish, and most reptiles show no clear signs of REM sleep, the type associated with dreaming in humans. Only birds and mammals, which appeared later in the evolutionary timeline of the animal kingdom, have full-blown REM Sleep. It suggests that dream REM sleep is the new kid on the evolutionary block. REM sleep seems to have emerged to support functions that NREM sleep alone could not accomplish, or that REM sleep was more efficient at accomplishing. Yet as with so many things in sleep, there is another anomaly. I said that all mammals have REM sleep, but debate surrounds cetaceans, or aquatic mammals. Certain of these ocean-faring species, such as dolphins and killer whales, buck the
REM sleep trend in mammals.
They don't have any. Although there is one case in 1969 suggesting that a pilot whale was in REM sleep for 6 minutes, most of our assessments to date have not discovered REM sleep, or at least what many sleep scientists would believe to be true REM sleep, in aquatic mammals. From one perspective, this makes sense. When an organism enters REM sleep, the brain paralyzes the body, turning it limp and immobile. Swimming is vital for aquatic mammals, since they must surface to breathe. If full paralysis was to take hold during sleep, they could not swim and would drown. The mystery deepens when we consider pinnipeds, one of my all-time favorite words, from the Latin derivatives, pinna, fin, and pedis, foot, such as fur seals. Partially aquatic mammals, they split their time between land and sea. When on land, they have both NREM sleep and REM sleep, just like humans and all other terrestrial mammals and birds. But when they enter the ocean, they stop having
REM sleep almost
entirely. Seals in the ocean will sample but a soupçon of the stuff, racking up just 5 to 10% of the REM sleep amounts they would normally enjoy when on land. Up to 2 weeks of ocean-bound time have been documented without any observable REM sleep in seals, who survive in such times on a snooze diet of NREM sleep. These anomalies do not necessarily challenge the usefulness of REM sleep. Without doubt, REM sleep, and even dreaming, appears to be highly useful and adaptive in those species that have it, as we shall see in Part 3 of the book. That REM sleep returns when these animals return to land, rather being done away with entirely, affirms this. It is simply that REM sleep does not appear to be feasible or needed by aquatic mammals when in the ocean. During that time, we assume they make do with lowly NREM sleep, which, for dolphins and whales, may always be the case. Personally, I don't believe aquatic mammals, even cetaceans like dolphins and whales, have a total absence of REM sleep, though several of my scientific colleagues will tell you I'm wrong. Instead, I think the form of REM sleep these mammals obtain in the ocean is somewhat different and harder to detect, be it brief in nature, occurring at times when we have not been able to observe it, or expressed in ways or hiding in parts of the brain that we have not yet been able to measure. In defense of my contrarian point of view, I note that it was once believed that egg-laying mammals, monotremes, such as the spiny anteater and the duck-billed platypus, did not have REM sleep. It turned out that they do, or at least a version of it. The outer surface of their brain, the cortex, from which most scientists measure sleeping brainwaves, does not exhibit the choppy, chaotic characteristics of REM sleep activity. But when scientists looked a little deeper, beautiful bursts of REM sleep electrical brainwave activity were found at the base of the brain, waves that are a perfect match for those seen in all other mammals. If anything, the duck-billed platypus generates more of this kind of electrical REM sleep activity than any other mammal. So they did have REM sleep after all. Or at least a beta version of it, first rolled out in these more evolutionarily ancient mammals. A fully operational, whole-brain version of REM sleep appears to have been introduced in more developed mammals that later evolved.
I believe a
similar story of atypical, but nevertheless present, REM sleep will ultimately be observed in dolphins and whales and seals when in the ocean. After all, absence of evidence is not evidence of absence. More intriguing than the poverty of REM sleep in this aquatic corner of the mammalian kingdom is the fact that birds and mammals evolved separately.
REM sleep may therefore have been birthed
twice in the course of evolution, once for birds and once for mammals. A common evolutionary pressure may still have created REM sleep in both, in the same way that eyes have evolved separately and independently numerous times across different phyla throughout evolution. Fourth common purpose of visual perception. When a theme repeats in evolution, and independently across unrelated lineages, it often signals a fundamental need. However, a very recent report has suggested that a protoform of REM sleep exists in an Australian lizard, which, in terms of the evolutionary timeline, predates the emergence of birds and mammals. If this finding is replicated, it would suggest that the original seed of REM sleep was present at least 100 million years earlier than our original estimates. This common seed in certain reptiles may have then germinated into the full form of REM sleep we now see in birds and mammals, including humans. Regardless of when true REM sleep emerged in evolution, we are fast discovering why REM sleep dreaming came into being, what vital needs it supports in the warm-blooded world of birds and mammals, e.g., cardiovascular health, emotional restoration, memory association, creativity, body temperature regulation, and whether other species dream. As we will later discuss, it seems they do. Setting aside the issue of whether all mammals have REM sleep, an uncontested fact is this: NREM sleep was first to appear in evolution. It is the original form that sleep took when stepping out from behind evolution's creative curtain, a true pioneer. This seniority leads to another intriguing question, a donné that I get asked in almost every public lecture I give: which type of sleep, NREM or REM sleep, is more important? Which do we really need? There are many ways you can define importance or need, and thus numerous ways of answering the question. But perhaps the simplest recipe is to take an organism that has both sleep types, bird or mammal, and keep it awake all night and throughout the subsequent day. NREM and REM sleep are thus similarly removed, creating the conditions of equivalent hunger for each sleep stage. The question is, which type of sleep will the brain feast on when you offer it the chance to consume both during a recovery night? NREM and REM sleep in equal proportions? Or more of one than the other, suggesting greater importance of the sleep stage that dominates? This experiment has now been performed many times on numerous species of birds and mammals, humans included. There are two clear outcomes. First, and of little surprise, sleep duration is far longer on the recovery night, 10 or even 12 hours in humans, than during a standard night without prior deprivation. 8 hours for us. Responding to the debt, we are essentially trying to sleep it off, the technical term for which is a sleep rebound. Second, NREM sleep rebounds harder. The brain will consume a far larger portion of deep NREM sleep than of REM sleep on the first night after total sleep deprivation, expressing a lopsided hunger. Despite both sleep types being on offer at the finger buffet of recovery sleep, the brain opts to heap much more deep NREM sleep onto its plate. In the battle of importance, NREM sleep therefore wins. Or does it? Not quite. Should you keep recording sleep across a second, third, and even fourth recovery night, there's a reversal. Now REM sleep becomes the primary dish of choice with each returning visit to the recovery buffet table, with a side of NREM sleep added. Both sleep stages are therefore essential. We try to recover one, NREM, a little sooner than the other, REM, but make no mistake, the brain will attempt to recoup both, trying to salvage some of the losses incurred. It is important to note, however, that regardless of the amount of recovery opportunity, the brain never comes close to getting back all the sleep it has lost. This is true for total sleep time, just as it is for NREM sleep and for REM sleep. That humans, and all other species, can never sleep back that which we have previously lost is one of the most important take-homes of this book, the saddening consequences of which I will describe in chapters 7 and 8, if only humans could. A third striking difference in sleep across the animal kingdom is the way in which we all do it. Here, the diversity is remarkable and, in some cases, almost impossible to believe. Take cetaceans, such as dolphins and whales, for example. Their sleep, of which there is only NREM, can be unihemispheric, meaning they will sleep with half a brain at a time. One half of the brain must always stay awake to maintain life-necessary movement in the aquatic environment. But the other half of the brain will, at times, fall into the most beautiful NREM sleep. Deep, powerful, rhythmic, and slow brainwaves will drench the entirety of one cerebral hemisphere, yet the other half of the cerebrum will be bristling with frenetic, fast brainwave activity, fully awake. This despite the fact that both hemispheres are heavily wired together with thick crisscross fibers, and sit mere millimeters apart, as in human brains. Of course, both halves of the dolphin brain can be, and frequently are, awake at the very same time, operating in unison. But when it is time for sleep, the two sides of the brain can uncouple and operate independently, one side remaining awake while the other side snoozes away. After this, one half of the brain has consumed its fill of sleep, they switch, allowing the previously vigilant half of the brain to enjoy a well-earned period of deep NREM slumber. Even with half of the brain asleep, dolphins can achieve an impressive level of movement and even some vocalized communication. The neural engineering and tricky architecture required to accomplish this staggering trick of oppositional lights on, lights off brain activity is rare. Surely Mother Nature could have found a way to avoid sleep entirely under the extreme pressure of non-stop 24/7 aquatic movement. Would that not have been easier than masterminding a convoluted split-shift system between brain halves for sleep, while still allowing for a joint operating system where both sides unite when awake? Apparently not. Sleep is of such vital necessity that no matter what the evolutionary demands of an organism, even the unyielding need to swim in perpetuum from birth to death, Mother Nature had no choice. Sleep with both sides of the brain, or sleep with just one side and then switch. Both are possible, but sleep you must. Sleep is non-negotiable. The gift of split-brain deep NREM sleep is not entirely unique to aquatic mammals. Birds can do it too. However, there is a somewhat different, though equally life-preserving, reason. It allows them to keep an eye on things, quite light rally. When birds are alone, one half of the brain and its corresponding, opposite side eye must stay awake, maintaining vigilance to environmental threats. As it does so, the other eye closes, allowing its corresponding half of the brain to sleep. Things get even more interesting when birds group together. In some species, many of the birds in a flock will sleep with both halves of the brain at the same time. How do they remain safe from threat? The answer is truly ingenious. The flock will first line up in a row. With the exception of the birds at each end of the line, the rest of the group will allow both halves of the brain to indulge in sleep. Those at the far left and right ends of the row aren't so lucky. They will enter deep sleep with just one half of the brain opposing in each, leaving the corresponding left and right eye of each bird wide open. In doing so, they provide full panoramic threat detection for the entire group, maximizing the total number of brain halves that can sleep within the flock. At some point, the two end guards will stand up, rotate 180 degrees, and sit back down, allowing the other side of their respective brains to enter deep sleep. We mere humans and a select number of other terrestrial mammals appear to be far less skilled than birds and aquatic mammals, unable as we are to take our medicine of NREM sleep in half-brain measure. Or are we? Two recently published reports suggest humans have a very mild version of unihemispheric sleep, one that is drawn out for similar reasons. If you compare the electrical depth of the deep NREM slow brainwaves and one half of someone's head relative to the other when they are sleeping at home, they are about the same. But if you bring that person into a sleep laboratory, or take them to a hotel, both of which are unfamiliar sleep environments, one half of the brain sleeps a little lighter than the other, as if it's standing guard with just a tad more vigilance due to the potentially less safe context that the conscious brain has registered while awake. The more nights an individual sleeps in the new location, the more similar the sleep is in each half of the brain. It is perhaps the reason why so many of us sleep so poorly the first night in a hotel room. This phenomenon, however, doesn't come close to the complete division between full wakefulness and truly deep NREM sleep achieved by each side of birds and dolphins' brains. Humans always have to sleep with both halves of our brain in some state of NREM sleep. Imagine, though, the possibilities that would become available if only we could rest our brains, one half at a time. I should note that REM sleep is strangely immune to being split across sides of the brain, no matter who you are. All birds, irrespective of the environmental situation, always sleep with both halves of the brain during REM sleep. The same is true for every species that experiences dream sleep, humans included. Whatever the functions of REM sleep dreaming, and there appear to be many, they require participation of both sides of the brain at the same time, and to an equal degree. Under pressure, the fourth and final difference in sleep across the animal kingdom is the way in which sleep patterns can be diminished under rare and very special circumstances, something that the U.S. government sees as a matter of national security, and has spent sizable taxpayer dollars investigating. The infrequent situation happens only in response to extreme environmental pressures or challenges. Starvation is one example. Place an organism under conditions of severe famine, and foraging for food will supersede sleep. Nourishment will, for a time, push aside the need for sleep, though it cannot be sustained for long. Starve a fly and it will stay awake longer, demonstrating a pattern of food-seeking behavior. The same is true for humans. Individuals who are deliberately fasting will sleep less as the brain is tricked into thinking that food has suddenly become scarce. Another rare example is the joint sleep deprivation that occurs in female killer whales and their newborn calves. Female killer whales give birth to a single calfons every 3 to 8 years. Calving normally takes place away from the other members of the pod. This leaves the newborn calf incredibly vulnerable during the initial weeks of life, especially during the return to the pod as it swims beside its mother. Up to 50% of all new calves are killed during this journey home. It is so dangerous, in fact, that neither mother nor calf appear to sleep while in transit. No mother-calf pair that scientists have observed shows signs of robust sleep en route. This is especially surprising in the calf, since the highest demand and consumption of sleep in every other living species is in the first days and weeks of life, as any new parent will tell you. Such is the egregious peril of long-range ocean travel that these infant whales will reverse an otherwise universal sleep trend, yet the most incredible feat of deliberate sleep deprivation belongs to that of birds during transoceanic migration. During this climate-driven race across thousands of miles, entire flocks will fly for many more hours than is normal. As a result, they lose much of the stationary opportunity for plentiful sleep. But even here, the brain has found an ingenious way to obtain sleep. In flight, migrating birds will grab remarkably brief periods of sleep lasting only seconds in duration. These ultra-power naps are just sufficient to avert the ruinous brain and body deficits that would otherwise ensue from prolonged total sleep deprivation. If you're wondering, humans have no such similar ability. The white-crowned sparrow is perhaps the most astonishing example of avian sleep deprivation during long-distance flights. This small, quotidian bird is capable of a spectacular feat that the American military has spent millions of research dollars studying. The sparrow has an unparalleled, though time-limited, resilience to total sleep deprivation, one that we humans could never withstand. If
you sleep-deprive this
sparrow in the laboratory during the migratory period of the year, when it would otherwise be in flight, it suffers virtually no ill effects whatsoever. However, depriving the same sparrow of the same amount of sleep outside this migratory time window inflicts a maelstrom of brain and body dysfunction. This humble passerine bird has evolved an extraordinary biological cloak of resilience to total sleep deprivation, one that it deploys only during a time of great survival necessity. You can now imagine why the US government continues to have a vested interest in discovering exactly what that biological suit of armor is. Their hope for developing a 24-hour soldier. How should we sleep? Humans are not sleeping the way nature intended. The number of sleep bouts, the duration of sleep, and when sleep occurs have all been comprehensively distorted by modernity. Throughout developed nations, most adults currently sleep in a monophasic pattern, that is, we try to take a long, single bout of slumber at night, the average duration of which is now less than 7 hours. Visit cultures that are untouched by electricity and you often see something rather different. Hunter-gatherer tribes, such as the Gabra in northern Kenya or the San people in the Kalahari Desert, whose way of life has changed little over the past thousands of years, sleep in a biphasic pattern. Both these groups take a similarly longer sleep period at night. 7 to 8 hours of time in bed, achieving about 7 hours of sleep, followed by a 30 to 60-minute nap in the afternoon. There is also evidence for a mix of the two sleep patterns, determined by time of year. Pre-industrial tribes, such as the Hadza in northern Tanzania or the San of Namibia, sleep in a biphasic pattern in the hotter summer months, incorporating a 30 to 40-minute nap at high noon. They then switch to a largely monophasic sleep pattern during the cooler winter months. Even when sleeping in a monophasic pattern, the timing of slumber observed in pre-industrialized cultures is not that of our own, contorted making. On average, these tribespeople will fall asleep 2 to 3 hours after sunset. Around 9 p.m., their nighttime sleep bouts will come to an end just prior to, or soon after, dawn. Have you ever wondered about the meaning of the term midnight? It of course means the middle of the night, or, more technically, the middle point of the solar cycle. And so it is for the sleep cycle of hunter-gatherer cultures, and presumably all those that came before. Now consider our cultural sleep norms. Midnight is no longer midnight. For many of us, midnight is usually the time when we consider checking our email one last time, and we know what often happens in the protracted thereafter. Compounding the problem, we do not then sleep any longer into the morning hours to accommodate these later sleep onset times. We cannot. Our circadian biology, and the insatiable early morning demands of a post-industrial way of life, denies us the sleep we vitally need. At one time we went to bed in the hours after dusk and woke up with the chickens. Now many of us are still waking up with the chickens, but dusk is simply the time we're finishing up at the office, with much of the waking night to go. Moreover, few of us enjoy a full afternoon nap, further contributing to our state of sleep bankruptcy. The practice of biphasic sleep is not cultural in origin, however. It is deeply biological. All humans, irrespective of culture or geographical location, have a genetically hardwired dip in alertness that occurs in the mid-afternoon hours. Observe any post-lunch meeting around a boardroom table and this fact will become evidently clear. Like puppets whose control strings were let loose, then rapidly pulled taut, heads will start dipping then quickly snap back upright. I'm sure you've experienced this blanket of drowsiness that seems to take hold of you, mid-afternoon, as though your brain is heading toward an unusually early bedtime. Both you and the meeting attendees are falling prey to an evolutionarily imprinted lull in wakefulness that favors an afternoon nap, called the postprandial alertness dip, from the Latin prandium, meal. This brief descent from high-degree wakefulness to low-level alertness reflects an innate drive to be asleep and napping in the afternoon, and not working. It appears to be a normal part of the daily rhythm of life. Should you ever have to give a presentation at work, for your own sake, and that of the conscious state of your listeners, if you can, avoid the mid-afternoon slot, what becomes clearly apparent when you step back from these details is that modern society has divorced us from what should be a preordained arrangement of biphasic sleep, one that our genetic code nevertheless tries to rekindle every afternoon. The separation from biphasic sleep occurred at, or even before, our shift from an agrarian existence to an industrial one. Anthropological studies of pre-industrial hunter-gatherers have also dispelled a popular myth about how humans should sleep. Around the close of the early modern era, circa late 17th and early 18th centuries, historical texts suggest that Western Europeans would take 2 long bouts of sleep at night, separated by several hours of wakefulness. Nestled in between these twin slabs of sleep, sometimes called first sleep and second sleep, they would read, write, pray, make love, and even socialize. This practice may very well have occurred during this moment in human history, in this geographical region. Yet the fact that no pre-industrial cultures studied to date demonstrate a similar nightly split shift of sleep suggests that it is not the natural, evolutionarily programmed form of human sleep. Rather, it appears to have been a cultural phenomenon that appeared and was popularized with the Western European migration. Furthermore, there is no biological rhythm of brain activity, neurochemical activity, or metabolic activity that would hint at a human desire to wake up for several hours in the middle of the night. Instead, the true pattern of biphasic sleep, for which there is anthropological, biological, and genetic evidence, and which remains measurable in all human beings to date, is one consisting of a longer bout of continuous sleep at night, followed by a shorter mid-afternoon nap. Accepting that this is our natural pattern of slumber, can we ever know for certain what types of health consequences have been caused by our abandonment of biphasic sleep? Biphasic sleep is still observed in several siesta cultures throughout the world, including regions of South America and Mediterranean Europe. When I was a child in the 1980s, I went on vacation to Greece with my family. As we walked the streets of the major metropolitan Greek cities we visited, there were signs hanging in storefront windows that were very different from those I was used to back in England. They stated, open from 9 a.m. to 1 p.m., closed from 1 to 5 p.m., open 5 to 9 p.m. Today, few of those signs remain in windows of shops throughout Greece. Prior to the turn of the millennium, there was increasing pressure to abandon the siesta-like practice in Greece. A team of researchers from Harvard University School of Public Health decided to quantify the health consequences of this radical change in more than 23,000 Greek adults, which contained men and women ranging in age from 20 to 83 years old. The researchers focused on cardiovascular outcomes, tracking the group across a 6-year period. The siesta practice came to an end for many of them. As with countless Greek tragedies, the end result was heartbreaking, but here in the most serious, literal way. None of the individuals had a history of coronary heart disease or stroke at the start of the study, indicating the absence of cardiovascular ill health. However, those that abandoned regular siestas went on to suffer a 37% increased risk of death from heart disease across the 6-year period, relative to those who maintained regular daytime naps. The effect was especially strong in working men, where the ensuing mortality risk of not napping increased by well over 60%. Apparent from this remarkable study is this fact: when we are cleaved from the innate practice of biphasic sleep, our lives are shortened. It is perhaps unsurprising that in the small enclaves of Greece where siestas still remain intact, such as the island of Ikaria, men are nearly 4 times as likely to reach the age of 90 as American males. These napping communities have sometimes been described as the places where people forget to die. From a prescription written long ago in our ancestral genetic code, the practice of natural biphasic sleep and a healthy diet appear to be the keys to a long sustained life. We are special. Sleep, as you can now appreciate, is a unifying feature across the animal kingdom. Yet within and between species there is remarkable diversity in amount, e.g., time, form, e.g., half brain, whole brain, and pattern, monophasic, biphasic, polyphasic. But are we humans special in our sleep profile, at least, in its pure form when unmolested by modernity? Much has been written about the uniqueness of Homo sapiens in other domains, our cognition, creativity, culture, and the size and shape of our brains. Is there anything similarly exceptional about our nightly slumber? If so, could this unique sleep be an unrecognized cause of these aforementioned accomplishments that we prize as so distinctly human, the justification of our hominid name, Homo sapiens, Latin derivative, wise person? As it turns out, we humans are special when it comes to sleep. Compared to old and New World monkeys, as well as apes, such as chimpanzees, orangutans, and gorillas, human sleep sticks out like the proverbial sore thumb. The total amount of time we spend asleep is markedly shorter than all other primates, 8 hours, relative to the 10 to 15 hours of sleep observed in all other primates, yet we have a disproportionate amount of REM sleep, the stage in which we dream. Between 20 and 25% of our sleep time is dedicated to REM sleep dreaming, compared to an average of only 9% across all other primates. Where the anomalous data point when it comes to sleep time and dream time
relative to all other monkeys and apes.
To understand how and why our sleep is so different is to understand the evolution of ape to man. From tree to ground, humans are exclusive terrestrial sleepers. We catch our Z's lying on the ground, or sometimes raised a little off it, on beds. Other primates will sleep arboreally, on branches or in nests. Only occasionally will other primates comb out of trees to sleep on the ground. Great apes, for example, will build an entirely new treetop sleep nest, or platform, every single night. Imagine having to set aside several hours each evening after dinner to construct a new IKEA bed frame before you can sleep. Sleeping in trees was an evolutionarily wise idea, up to a point. It provided safe haven from large, ground-hunting predators, such as hyenas, and small blood-sucking arthropods, including lice, fleas, and ticks. But when sleeping 20 to 50 feet up in the air, one has to be careful. Become too relaxed in your sleep depth when slouched on a branch or in a nest, and a dangling limb may be all the invitation gravity needs to bring you hurtling down to earth in a life-ending fall, removing you from the gene pool. This is especially true for the stage of REM sleep, in which the brain completely paralyzes all voluntary muscles of the body, leaving you utterly limp, a literal bag of bones with no tension in your muscles. I'm sure you have never tried to rest a full bag of groceries on a tree branch, but I can assure you it's far from easy. Even if you manage the delicate balancing act for a moment, it doesn't last long. This body balancing act was the challenge and danger of tree sleeping for our primate forebears, and it markedly constrained their sleep. Homo erectus, the predecessor of Homo sapiens, was the first obligate biped, walking freely upright on two legs. We believe that Homo erectus was also the first dedicated ground sleeper. Shorter arms and an upright stance made tree living and sleeping very unlikely. How did Homo erectus, and by inference, Homo sapiens, survive in the predator-rich ground sleeping environment, when leopards, hyenas, and saber-toothed tigers, all of which can hunt at night, are on the prowl, and terrestrial bloodsuckers abound? Part of the answer is fire. While there remains some debate, many believe that Homo erectus was the first to use fire, and fire was one of the most important catalysts, if not the most important, that enabled us to come out of the trees and live on terra firma. Fire is also one of the best explanations for how we were able to sleep safely on the ground. Fire would deter large carnivores, while the smoke provided an ingenious form of nighttime fumigation, repelling small insects ever keen to bite into our epidermis. Fire was no perfect solution, however, and ground sleeping would have remained risky. An evolutionary pressure to become qualitatively more efficient in how we sleep therefore developed. Any Homo erectus capable of accomplishing more efficient sleep would likely have been favored in survival and selection. Evolution saw to it that our ancient form of sleep became somewhat shorter in duration, yet increased in intensity, especially by enriching the amount of REM sleep we packed into the night. In fact, as is so often the case with Mother Nature's brilliance, the problem became part of the solution. In other words, the act of sleeping on solid ground, and not on a precarious tree branch, was the impetus for the enriched and enhanced amounts of REM sleep that developed, while the amount of time spent asleep was able to modestly decrease. When sleeping on the ground, there's no more risk of falling. For the first time in our evolution, hominids could consume all the body immobilized REM sleep dreaming they wanted, and not worry about the lasso of gravity whipping them down from treetops. Our sleep, therefore, became concentrated, shorter and more consolidated in duration, packed plenty with high-quality sleep. And not just any type of sleep, but REM sleep that bathed the brain rapidly accelerating in complexity and connectivity. There are species that have more total REM time than hominids, but there are none who power up and lavish such vast proportions of REM sleep onto such a complex, richly interconnected brain as we Homo sapiens do. From these clues, I offer a theorem, the tree-to-ground re-engineering of sleepwash, a key trigger that rocketed Homo sapiens to the top of evolution's lofty pyramid. At least two features define human beings relative to other primates. I posit that both have been beneficially and causally shaped by the hand of sleep, and specifically our intense degree of REM sleep relative to all other mammals, 1. Our degree of sociocultural complexity, and 2. Our cognitive intelligence.
REM sleep,
and the act of dreaming itself, lubricates both of these human traits. To the first of these points, we have discovered that REM sleep exquisite lyre calibrates and fine-tunes the emotional circuits of the human brain, discuss it in detail in Part 3 of the book. In this capacity, REM sleep may very well have accelerated the richness and rational control of our initially primitive emotions, a shift that I propose critically contributed to the rapid rise of Homo sapiens' dominance over all other species in key ways. We know, for example, that REM sleep increases our ability to recognize and therefore successfully navigate the kaleidoscope of socio-emotional signals that are abundant in human culture, such as overt and covert facial expressions, major and minor bodily gestures, and even mass group behavior. One only needs to consider disorders such as autism to see how challenging and different a social existence can be without these emotional navigation abilities being fully intact. Related, the REM sleep gift of facilitating accurate recognition and comprehension allows us to make more intelligent decisions and actions as a consequence. More specifically, the cool-headed ability to regulate our emotions. Each day, a key to what we call emotional IQ, depends on getting sufficient REM sleep night after night. If your mind immediately jumped to particular colleagues, friends, and public figures who lack these traits, you may well wonder about how much sleep, especially late morning REM-rich sleep, they are getting. Second, and more critical, if you multiply these individual benefits within and across groups and tribes, all of which are experiencing an ever-increasing intensity and richness of REM sleep over millennia, we can start to see how this nightly REM sleep recalibration of our emotional brains could have scaled rapidly and exponentially. From this REM sleep, enhanced emotional IQ emerged a new and far more sophisticated form of hominid socioecology across vast collectives, one that helped enable the creation of large, emotionally astute, stable, highly bonded, and intensely social communities of humans. I will go a step further and suggest that this is the most influential function of REM sleep in mammals, perhaps the most influential function of all types of sleep in all mammals, and even the most eminent advantage ever gifted by sleep in the annals of all planetary life. The adaptive benefits conferred by complex emotional processing are truly monumental, and so often overlooked. We humans can instantiate vast numbers of emotions in our embodied brains, and thereafter deeply experience and even regulate those emotions. Moreover, we can recognize and help shape the emotions of others. Through both of these intra- and interpersonal processes, we can forge the types of cooperative alliances that are necessary to establish large social groups, and beyond groups, entire societies brimming with powerful structures and ideologies. What may at first blush have seemed like a modest asset awarded by REM sleep to a single individual is, I believe, one of the most valuable commodities ensuring the survival and dominance of our species as a collective. The second evolutionary contribution that the REM sleep dreaming state fuels is creativity. NREM sleep helps transfer and make safe newly learned information into long-term storage sites of the brain. But it is REM sleep that takes these freshly minted memories and begins colliding them with the entire back catalog of your life's autobiography. These mnemonic collisions during REM sleep spark new creative insights as novel links are forged between unrelated pieces of information. Sleep cycle by sleep cycle, REM sleep helps construct vast associative networks of information within the brain.
REM sleep
Can even take a step back, so to speak, and divine overarching insights and gist, something akin to general knowledge, that is, what a collection of information means as a whole, not just an inert back catalog of facts. We can awake the next morning with new solutions to previously intractable problems. Or even be infused with radically new and original ideas, adding, then, to the opulent and domineering socio-emotional fabric that REM sleep helps weave across the masses came this second, creativity benefit of dream sleep. We should cautiously revere how superior our hominid ingenuity is relative to that of any of our closest rivals, primate or other. The chimpanzees, our nearest living primate relatives, have been around approximately 5 million years longer than we have. Some of the great apes preceded us by at least 10 million years. Despite eons of opportunity time, neither species has visited the moon, created computers, or developed vaccines. Humbly, we humans have. Sleep, especially REM sleep and the act of dreaming, is a tenable, yet underappreciated, factor underlying many elements that form our unique human ingenuity and accomplishments, just as much as language or tool use. Indeed, there is even evidence that sleep causally shapes both these latter traits as well. Nevertheless, the superior emotional brain gifts that REM sleep affords should be considered more influential in defining our hominid success than the second benefit, of inspiring creativity. Creativity is an evolutionarily powerful tool, yes, but it is largely limited to an individual. Unless creative, ingenious solutions can be shared between individuals through the emotionally rich, pro-social bonds and cooperative relationships that REM sleep fosters, then creativity is far more likely to remain fixed within an individual, rather than spread to the masses. Now we can appreciate what I believe to be a classic, self-fulfilling positive cycle of evolution. Our shift from tree to ground sleeping instigated an ever more bountiful amount of relative REM sleep compared with other primates, and from this bounty emerged a steep increase in cognitive creativity, emotional intelligence, and thus social complexity. This, alongside our increasingly dense, interconnected brains, led to improved daily and nightly survival strategies. In turn, the harder we worked those increasingly developed emotional and creative circuits of the brain during the day, the greater was our need to calibrate these ever-demanding neural systems at night with more REM sleep. As this positive feedback loop took hold in exponential fashion, we formed organized, maintained, and deliberatively shaped ever larger social groups. Their rapidly increasing creative abilities could thus be spread more efficiently and rapidly, and even improved by that ever-increasing amount of hominid REM sleep. That enhances emotional and social sophistication. REM sleep dreaming therefore represents a tenable new contributing factor, among others, that led to our astonishingly rapid evolutionary rise to power, for better and worse, a new, sleep-fueled, globally dominant social superclass.